Okay, let's get going. This is Craig Hartman, and I appreciate all of you that tune in. I enjoy doing these. I also enjoy attending other ones. We are going to do VFD Theory today, and next session, we'll let you know when that is due to the July 4th holiday and so on. But the next session, we will do startup maintenance and troubleshooting of VFDs, and we'll actually go out in our lab and have one of our techs go through that. And then we'll have harmonics. We talked about active harmonic correction before, but in the harmonics, VFD harmonics, we'll talk about every single method of harmonic correction that is available on VFDs, and we will talk about the advantages and disadvantages of each, show you some real-world testing results, and we will, of course, cover IEEE 519 and introduce the subject of harmonics. So today, VFD theory, my little icebreaker, when was the microprocessor invented? The answer is 1969. Now, 1969 was also the year of Woodstock, and it's the year that the Manson family paid a visit to the Tate residence. But the big event that I think is very interesting is that we landed on the moon. Now, it turns out that the microprocessor was invented in 1969, but wasn't really on sale to the public until a couple of years later. And so we were landing on the moon before we really had microprocessors available. I think that's very interesting. This is the first real computer. We call it a Turing complete computer. So I have some information there, and then I have some other information on the Enigma, which is in World War II, and how that affects, or how that relates to Alan Turing. Don't have time to get into that too much, so, but if you download the presentation, you can take a look at that. So, definitions. There's the definition of adjustable speed drive, and the definition for the adjustable speed drive system. As I mentioned last time, we will have a number of slides in there that have specifically to do with the National Electrical Code. I am not going to cover those in great detail, but I will talk a little bit about NEC as it relates to variable frequency drives. So let's talk about how they work. Well, Tesla gave us the three-phase system of power generation, transmission, distribution. And so we are going to assume that our particular drive here is 480 volts. It's pretty common voltage for drives. And then we have 6 diodes. Now, I am going to talk about those diodes as check valves because I've been in this business a lot of years. I'm an electrical engineer, but I still think somewhat in terms of electricity as it compares to water systems. And so I'll be talking about this as if it were a water system. These diodes are simply check valves. They let current flow in one direction. Which direction? Well, the direction of the arrow. So whenever A phase is most positive, then that check valve will open up and it will let current flow through A phase. When A phase begins to go down and B phase becomes the most positive, then the B phase check valve will open it up and the current will then flow onto the DC bus. The same happens on the negative side. So we get this three-phase, and basically what it's doing is letting the most positive portions of the AC wave through to the positive DC bus, and the most negative portions of the AC wave go through and end up on the negative bus. Now, if we measure the voltage between the negative bus and the positive bus, it looks like this here that I have blown up. You'll notice that when I blew it up, I changed the scaling. So it starts at 580 volts. So the bottom of that waveform is about 587 volts, and the top of the waveform about 680 volts. So we have rectified AC to DC. The problem is we still have some AC ripple current on there. So how do you get rid of AC ripple current? Well, if it was in a plumbing system, you might add a reservoir. So that's exactly what we do, is add a reservoir. A reservoir in electrical terms, of course, is a capacitor. So we've got these pulses of current coming in, and the pulses of current are really the problem with drives as far as harmonics go, and we will talk about that in a couple more sessions. But when these pulses of current go into the reservoir fills up to a level about 650 volts. Now that will go down a little bit as you load the drive. It can be affected by line reactors and so on, but 650 volts is an approximate value that you would see on the DC bus. So that DC bus charges to 650 volts, and with the reservoir there, it becomes very smooth. The purpose of the capacitor is to smooth that out. So the thing that's actually running our motor is not the AC system, it is the capacitor. All of the power coming from the drive to the motor comes from that capacitor, and then this AC to DC converter is responsible for keeping that capacitor charged. Now we need to, we have a pre-charge circuit in there. I won't mention too much about this, except to say that when you first energize the drive, you can have very, very high currents into the capacitor because it looks like a short circuit. So all drives have pre-charge circuits, and this is a simple pre-charge circuit composed of a resistor and a contactor. So the capacitor charges through the resistor that limits the current into the capacitor. It keeps you from tripping breakers and fuses, but most importantly, it keeps you from blowing up the capacitor. And then after the capacitor reaches its rated voltage, then we bypass that. And at that point, then the pre-charge circuit basically is not in the circuit. If the pre-charge circuit fails, we will talk about that, how to determine that in our next session. Now what we need to do is to power the motor. So here we have a switch. If we close this switch, then it will cause the A phase of the motor to go positive. If we close this switch, it will cause the A phase of the motor to go negative. So we simply turn that on and off in order to create a pulsed waveform to the motor. Now, it's not a great waveform. I wish we had a better waveform to the motor, but that's not the way it works. There have been a number of drive technologies in the past, but in low voltage, pretty much all drives these days are pulse width modulated. So we will talk about that in a moment. Now, I should mention that I'm showing this as a switch. Of course, you know that because it has to switch thousands of times a second, that is actually an IGBT, an insulated gate bipolar transistor, but it operates just like a switch. It just turns on and off. You should never use power factor capacitors on the load side of a drive unless you'd like to buy another drive. Now here is your output to the motor. Now you can turn it on positive or you can turn it on negative, and thus you get an AC waveform. Now this is 650 volts, and therefore when you turn it on positive, you're always going to get 650 volts because that is the voltage on the DC bus, or negative 650 volts. Now we put 480 volts 60 hertz in, we get 480 volts 60 hertz out. We didn't really accomplish much. So let's change the frequency to 30 hertz. If you remember from our last seminar, when you change the frequency to half, you must change the voltage to half. That's because the volts per hertz must remain constant. The drive does this automatically for you, so you don't really need to know that much about it, but it's good to understand why that is. So we can simply turn these things on and off slower, and we will reduce the frequency. But how are we going to control the voltage? Well, there have been a number of drive technologies for controlling the voltage. Some of them which included changing the DC bus voltage level. But virtually all drives these days, low voltage drives, are PWM. And so PWM looks like this. Now, if I go to half speed, then I have to go to half voltage. The way I get that is to turn it on half the time and off half the time. So as you can see, we still have 650 volts. But if we turn it on half the time, off half the time, on half the time, off half the time, on half the time, off half the time, we will get effectively half of the voltage. Now, what if we want to go to 10 hertz? Well, if we go to 10 hertz, now that is 1/6 of 60. Therefore, the voltage has to be 1/6 of 480 volts. And now you will notice that the pulses need to be on only 1/6 of the time and off 5/6 of the time. And if we do that, we have an effective voltage of 80 volts. Notice here that the blue waveforms are simply AC sine waves of that voltage and that frequency. I put them in there just for your reference, but you don't get that out of the drive. What you get out of the drive is what we call this picket fence effect. And when you go positive or negative, controls the frequency of the motor, and with the number of pulses and how long they're on and how long they're off, or I might say the width of the pulses, is how you control the voltage. So we call that pulse width modulation. Now notice that there are two frequencies here. Let's go down here to this 10 hertz waveform. One frequency is the 10 hertz, and you can see we have one cycle of 10 hertz on my little graph here, or my waveform. But there is another frequency. That is the frequency of the pulses. So we have 10 hertz, and we've got, in my graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 pulses in each cycle. 12 pulses per cycle times 10 cycles per second gives you 120 pulses per second. And that frequency is called our carrier frequency. So the waveforms that I showed you, I just did on the computer. Now let's look at some real waveforms on a real drive. Now I've selected a carrier frequency of 1 kilohertz. I have seen, at least years ago, some drives that did not let you select the carrier frequency, but I would dare say that pretty much any drive any of you have, that carrier frequency comes programmed from the factory at a certain value, but you can change that, you can program that. So I selected a carrier frequency of 1 kilohertz. Remember, this is a real variable frequency drive and an oscilloscope tracing. The top graph is at no load, the bottom graph is at full load. So you'll notice we get the voltage is this blue, this dark blue, that's your PWM waveform. The current is in the magenta color, so the voltage never looks sinusoidal. It just looks like a picket fence. The current, on the other hand, starts kind of looking sinusoidal. And so this is not a good waveform. You shouldn't take a variable frequency drive and use it to power your house or a lighting system or a computer. Just motors. But those motors operate very well on the PWM waveform. Now let's change the carrier frequency. That's 1 kilohertz. This is 5 kilohertz. Well, let's change it to 10 kilohertz. And there is 10 kilohertz. Remember, these are actual oscilloscope tracings from a real variable frequency drive. So would you rather have 1 kilohertz, 5 kilohertz, or 10 kilohertz? Well, let's learn a little bit about that. What are the advantages of high carrier frequency? The higher the carrier frequency, the lower the acoustic noise. You know that drives tend to sing. They have that kind of ee kind of noise. That noise is at the carrier frequency. And if you change the carrier frequency, that noise will change. And the higher the carrier frequency in general, the lower the noise level. So by increasing the carrier frequency, that drive will become quieter. Again, not the drive itself, but the motor operating on the drive will be quieter. And as you can see, you get a slightly improved motor waveform. And there's some other things in there that you can read later. So that sounds good. Let's just hike that carrier frequency all the way up, unless there are disadvantages. Well, there are some disadvantages of higher carrier frequency. The biggest one is lower VFD efficiency. Every time you switch those transistors on and off, they generate a little bit of heat. And the faster you switch them on and off, the more heat is created. And you could, if you go to the highest carrier frequency of the drive, you may find that you have 4 times as much heat being generated in the drive as at a lower carrier frequency. So that causes increased VFD heating. It can shorten the VFD life. It may require derating of a VFD. For instance, a lot of drives can go up to, say, 14, 15 kilohertz. in 1, 2, 3 horsepower. But when you get into hundreds of horsepower, they can't do that because at those carrier frequencies, they just generate so much heat that they can't get rid of it. So you actually have to derate them. And you can see higher overshoot peak voltages and so on. It also increases bearing currents in your motor. So if you look at those two, there tend to be more disadvantages than advantages of high carrier frequency. My advice, and I think this is advice pretty much that any variable frequency drive manufacturer would give you, is go down to around 2.5 kilohertz. At 2.5 kilohertz, you're kind of hitting that optimum point where you're getting the advantages of high carrier frequency, but you don't get the disadvantages of high carrier frequency. The only time that I would go higher than that is if my motor was very, very noisy, in which case I would maybe go to 3 kilohertz, maybe even 4 kilohertz, see what it sounds like. We did a hospital at one point. I had 45 drives. The manufacturer sent the VFD at 8 kilohertz, and I went, this doesn't make any sense. I called them and I said, is this where you recommend it being? And they said, oh no, it should be down around 2 kilohertz. And I didn't say anything, but I thought, well, why did you ship it at 8? In any case, we set everything to 2 kilohertz. Then we went around the hospital when it was dead quiet. That's probably not a very good term to use in a hospital, but very quiet in the middle of the night. And we listened to the HVAC system. And there were 3 places where we could just barely hear that little bit of whine. And so we ended up setting those drives up to 4 kilohertz before that whine kind of went away and nobody could hear it. And so we left those 3 drives at 4 kilohertz and all of the others at 2 kilohertz. So that's one of the reasons. The other thing is if you have a filter on the output, like maybe a sine wave filter, and the sine wave filter manufacturer states the output frequency must be 5 kilohertz, well, then you do that. You follow their recommendation. This is NEC 430 Part X. That is the part that covers variable frequency drives. Now let's look at a real VFD. I like this one. These IGBT-based inverters were basically created by the Japanese and came out in around 1987, 88. And this is one of those early vintage inverters. I like it because you can see all the parts. So right here in the lower half is your converter. You'll notice that you have 3 blocks and there are 2 diodes in each block. So 2 diodes here, 2 diodes here, 2 diodes here, and those rectify the AC to the DC. But we have a lot of ripple on the DC, and therefore we have to have these capacitors. In this case, we have 4 capacitors, but they just act like one capacitor. And you may have 1 capacitor in a drive, you may have 12 capacitors in a drive. It just depends upon how big the capacitors are and how much capacitance you need. By the way, if those capacitors are functioning correctly and the inverter is, or the converter is functioning correctly, you shouldn't get more than about 3 volts ripple on the DC bus. Now the DC bus comes over and here's 2 switches. Of course, they're IGBTs, 2 IGBTs in this block, 2 IGBTs in this block, 2 IGBTs in this block, and they create the output waveform. Now here's a circuit board. That's a circuit board in 1987. Big circuit boards, lots of parts. And digital drives were somewhat delayed because of the cost of these circuit boards. Now, I'm also showing you the transistor snubber. Those go on the transistors to help protect them. And then there's a capacitor precharge circuit. There's your resistor. There's a timer. Back then, we actually used a physical timer. These days, that's all solid state on the circuit board. And then we have the contactor. So there is the drive that we talked about, but we have now replaced those switches with IGBTs. Now this is a circa 2020 drive, and they're harder to see because generally they put the components on multiple levels in order to make the footprint of that drive as small as possible. So it's just not possible to see all the parts by simply looking at one picture. But you'll notice the circuit board, this circuit board, and I'm guessing at this point, I'm guessing that's probably about maybe 14 inches by 18 inches, something like that. Big circuit board This one's only like 3.5 inches by 5 inches, or maybe even a little bit smaller than that. All that circuitry is now surface mount, and it's got 2 very high-speed microprocessors. We would call them digital signal processors because they're built specifically for variable frequency drives. And this drive will run circles around the other one because of the incredible advances in solid-state microprocessors. But other than the microprocessor, this drive works the same way as it did in 1987. I find that fascinating that there really haven't been any significant advances in variable frequency drive topology, for low voltage at least, since 1987. Here's a drive in an enclosure. This one is convection cooled. This is conductor temperature ratings. Typically, your conductors into a drive need to be rated at 75 degrees. That's pretty common in most low voltage equipment. Here is a drive that is fan cooled. We really like fan cooled enclosures because they keep the drive clean. A drive like this should give you 20 years of life because that drive stays very clean on the inside. And we mount our filters right out here where you could see them rather than behind louvers, because we find that putting our filters behind louvers, people forget to change the filters. So obviously, if you have filters, you need them. If you want a really heavy-duty industrial drive, this is what you should get. Now, a lot of drives are going this way. They're just a drive mounted on the wall. They tend to not have the fans and filters, and they don't have the steel enclosure. They're cheaper and they're smaller. So, of course, those are both big advantages. I really prefer to have the steel enclosure so that you have room to mount things in there, and I believe that it's much better in an arc flash type situation. And the fans and filters. These drives tend to last probably 3 to 7 years, something like that. This drive should easily last 20 years. So even though it takes more space and it's a little more expensive, in the long run, it's probably less expensive. This is the front of our drive. It shows a high-performance keypad, and we put some of these lights in there. Not that they're necessary, but most people don't know how to operate the keypad. And so by putting these lights in there, it makes it very easy for people to know if the power's on and if the VFD is running, if there's a fault, and so on and so forth. Let's talk about ampacity of conductors. According to the National Electrical Code, when you have a motor with a service factor of 1.15 or greater, then the conductors, the overload protection can be set to trip up to 125%. And because of that, the National Electrical Code requires that conductors from the power system to the motor be sized at 125% of the motor amps. When you put a VFD in there, that does not change. The conductors between the VFD and the motor need to be sized at 125% of the motor full load amps. Now, we typically recommend setting the overload protection of the drive at 100% of the full load amps. So I really think this doesn't make total sense, but I certainly understand that they're trying to be safe. The drive could have a bypass in it. You never know if somebody could take the drive out. And so that remains a requirement that the output amps need, the cable needs to be rated for 125% of the motor amps from the motor to the VFD. Now, how about the cables coming into the VFD? By code, they are rated for also 125%, but there's rated for 125% of the input amps to the VFD. Well, what are the input amps to the VFD? It gets complicated. And being a VFD manufacturer, I really like that because I can say they are whatever I want them to be. Because if you have a passive harmonic filter, you have a 12-pulse drive, you have an 18-pulse drive, you have an active front end, you have reactors, all these things change the input amps to the drive. So most people actually just use the same cable and the output is on the input, and the input cable is 125% of the motor full load amps. I actually think that's fine. Now, if you go over 1,000 volts, that changes a little bit, and I'm not going to go through how this all happened. The NEC 2020 made it more confusing than the NEC 2017, but the fact is that the input to a drive over 1,000 volts needs to be 125% of the input amps to the drive. The output, however, the cable can just be sized to wherever the VFD is programmed to trip. So there is a difference there between medium voltage and low voltage VFDs. If you have a bypass device, then of course you have the ability to run the motor across the line, and then that 125% is the same, but still based on the National Electrical Code. This is one of my favorite pictures. I was teaching this class, and they gave me this picture. This drive has failed, and I'm going to show you the next slide, and let's see if you can figure out why it failed. Love that picture. Now, if you see up there on the top, there's a little hole. Somebody punched a conduit, a hole there for conduit, and either moved it or something, but there's a hole there, and a bird decided that would make a great home. If you want VFDs to last a long time, your religion should be keep them clean, keep them cool, and keep them dry. Those are the three rules of VFD longevity: keep them clean, keep them cool, and keep them dry. And having filters on a steel enclosure that protect your drive certainly keep that thing very clean, and also tend to keep it cool and dry. So little advice that is not rocket science, but something to think about. Here's a dissected VFD, shows all the parts inside. I'm not going to go into that in detail due to time. Here we have our three enclosures. The enclosures on the left are non-ventilated in terms of they're not forced ventilated, and they don't have filters on there. They're the cheapest ones, and they do have a steel enclosure, and so they're nice for arc flash and so on. But I recommend these ones over here in the middle because they're forced fan and filtered, and if you keep those filters clean, those drives are going to last a long, long time, and the inside of that enclosure is going to be very clean. The ones on the right, of course, are outdoor, and we do the same thing. We have fans and filters on our outdoor enclosures. We paint them white, and we have hoods, of course, over the filters to keep them clean and to keep rain and dirt and things from drifting into them. This is the interior of a NEMA 3R enclosure. This shows a couple of drives in a single enclosure. And I want to point out this has a harmonic filter. I'm not going to talk about harmonic filters until we get to our next session that we'll talk completely about harmonic filters. I do want to show you one thing. See over here where it says a DVDT filter? That's a DVDT filter. It's basically got a reactor on there, but it's also got a capacitor and resistors. Just want you to know what that looks like. We'll be talking about that momentarily. Here's a drive enclosure with 5 drives on it, and one of our shop people in there showing the inside of that enclosure. Here's a large regenerative conveyor line on an aggregate plant. Here's a dry dock pumping station. Notice that we have external air. This thing is ventilated with external outdoor air brought into the enclosure, which is inside, of course, to keep things clean. Here's a wastewater treatment plant with lots of drives in it. Here's another VFDs and a custom assembly. We do a lot of those. It has a PLC in there. It's got PLC I/O. It's got some other motor starters. It's got a surge protector. So very common to put multiple drives inside of a single enclosure. It's a potato processing facility. And this one is a drive that has an active filter, not an active front end, but an active filter. And we went ahead because this is, I guess, convenience for mounting. We went ahead and put the active filter actually inside the drive cabinet. So that's an active filter. And over here is the drive. There's a NEMA 3R custom enclosure. Here's one with a drive and 2 soft starts. And you'll notice in this case, the drive has the heat sinks poking out through the back of the enclosure. That's why you can get by with such small fans here. And if you look on the back, the heat sinks are poking out through the back of the enclosure. And that's a way of still keeping the interior very clean while allowing the outside fins to be cooled. It's a little picture from the bottom, and there it is on a pad. This is a pumping station. There's a large outdoor enclosure, and there's one in a fairly dusty facility. This has some stuff on the code, and you can read that. Basically saying you've got to have branch short circuit protection, and it talks a little bit about that. A drive can run multiple motors. If you run multiple motors on a drive, then obviously the drive doesn't know how much current is going into each of the motors. Therefore, you have to have separate overload protection and typically separate contactors on each motor. But this is a very common application. Here's the NEC again, talks about the depth of working space. Typically, we need 3.5 feet in front of the drive. Constant torque versus variable torque. There is no such thing at a variable frequency drive. All variable frequency drives are constant torque. The difference is that a variable frequency drive that is listed as variable torque has 110% overload for a minute. A variable frequency drive listed as constant torque has 150% overload for a minute. So both of them are actually constant torque, but if you buy a constant torque drive, you get more overload, and that overload can help you on typically constant torque applications. So a fan or a pump would typically be a variable torque application. 110% overload is fine. A conveyor would be a constant torque application. We'd prefer more like 150% overload. Now, you get constant torque up to 60 hertz, and then once you go above 60 hertz, you can increase the frequency, but you can't increase the voltage because you've only got 460 volts, and therefore the volts per hertz goes down and your torque capability goes down. This is an induction motor torque speed curve. I like to say that on a drive, motors never start, they only run. So this is the starting portion of the curve up to generally we say about 150% torque here. And your motor will never see that when running on a variable frequency drive. I'll show you that in a moment. If you go above base speed, then you basically just get a mirror image of that as we go above base speed. Now on a variable frequency drive, if you're at 60 hertz, you get this curve that gives you 1800 RPM. If you're at 50 hertz, you get this curve that gives you 1500 RPM and so on. So we're always operating on this portion of the torque speed curve. And when we just gradually increase the speed of that motor, it's always running. It never actually starts. Now, I don't have time to get into this too much, but above base speed, the whole torque speed curve tends to go down. So it goes down as the square of voltage because the torque capability, that whole torque curve, is proportional to the square of the volts per hertz, approximately. And so just wanted to show you what a graph of that would look like. If you get too high, you can get into very high currents, and you can actually stall the motor, as well as other problems due to vibration and so on, and bearings. But it's not uncommon to go a little bit above base speed, and I don't have any problem with that in general, as long as your equipment can take it, you don't get vibration, and you stay under the motor full load amps. These are some different control methods. We may get into that in a more advanced session in which we talk about various controls. But state-of-the-art drives now generally have sensorless vector control, which is really great stuff and requires a very high-speed microprocessor, or actually digital signal processor, that didn't used to be available. This shows you some of the different control types and the advantages and disadvantages of each. If you have open loop flux vector, you want to use it, then it requires that you actually tune the motor, and we may get into that later. Optimum excitation control actually looks at the load on the motor and adjusts the volts per hertz accordingly. So if you don't need full torque, it will actually reduce the volts per hertz, saves you a little bit of energy, not a lot, but it also tends to decrease vibration. So that's a feature, a lot of advanced drives. Now, power can go from the input of the drive to the motor in a variable frequency drive. It cannot go from the motor back to the line unless you have a regenerative front end or a regenerative converter. So a lot of times we put braking resistors on here so that if a motor has to slow down too fast, or if it is on a downhill slope, the power can go through the inverter, but then it gets stuck on the DC link. That causes the voltage to go up and it will trip on overvoltage. So we can put in a braking resistor in there to basically just waste all that power and prevent you from tripping. And this talks about the various braking methods. Now, want to talk a little bit about DVDT. There is a reflective wave phenomenon and there's a resonant circuit phenomenon. We're just going to look at some waveforms. This waveform is actually from a DVDT manufacturer, and I got that off their website. This is TCI. You'll notice that these pulses are at 650 volts, but every once in a while, you can have a resonant frequency or pulses lining up such that you get an overvoltage. Now, most motors that are not VFD rated are rated for 1,000 volts, and you can see that those pulses are going just a little bit more than 1,000 volts. That's with 70 feet of cable. With 500 feet of cable, we get voltages going way up. There's a carrier frequency of 2.5 kilohertz. If you go to 8 kilohertz, you can see the problem is worse. So that is why we always want to use a VFD rated motor. What is a VFD rated motor? Well, this is NEMA. NEMA MG1 Part 31 says a VFD rated motor should have 1,000 volt insulation to these spikes. A VFD rated motor has insulation that's 3.1 times the rated voltage. I'm just going to call that 1,600 volts because 1,600 volts is a very common VFD rated insulation. Whenever you have a VFD, always get a VFD rated motor, and this is the chief thing that defines what a VFD rated motor is. That is the premium insulation. It's also able to withstand higher rise times when we have that PWM waveform going on and off. Now, here is a motor nameplate. I've showed you this before if you were in our motor section. Notice that when you run a VFD, you always want to run a service factor motor. But when you run it on a VFD, you can't use the service factor. And the reason for that, as we looked at in our motor class, was when the motor slows down, the fan on the motor shaft slows down, the motor doesn't get as much cooling. Therefore, you use up your service factor in allowing the motor to run slower. This is a great nameplate. This is from US Motors. It actually has a nameplate for across the line and for inverter duty. So that's pretty nice. Most motor nameplates do not have that. So we simply use this, but we need to know that we cannot run a service factor motor at service factor when running on a VFD because of the loss of cooling at lower speeds. This shows you how to measure your DVDT. There are some drives that will allow you to go out to 1,600 feet, about 500 meters, without having a DVDT filter. And if you have one of those, then that's great. You don't need a DVDT filter. Our rule of thumb is, and let me, well, I'll tell you that in a moment. This is a Mitsubishi drive. In addition to allowing you to go to 1,600 meters, it also, instead of just running, let's say at 4 kilohertz frequency on the carrier frequency, which is what this graph shows, it actually varies that carrier frequency to prevent motor voltages from adding up and that or reflected voltages, but it also makes it sound a lot better because here's the acoustic waveform at 4 kilohertz. Here's the acoustic waveform again at 4 kilohertz, but with soft PWM introduced. So you get rid of that kind of metallic ringing. So we recommend a DVDT filter, and I showed it to you before. Anytime the motor is either not VFD rated or the cables between the motor and the drive are 100 feet or more. So again, you don't need the filter if you have a VFD rated motor and you have something like soft PWM. If you have not a VFD rated motor, I would recommend a DVDT filter, period. Other than that, anything over 100 feet, we recommend a DVDT filter. What it really does is prevent those voltages from going over 1,000 volts, which is the rating of the motor. Let's talk a little bit about motor bearings. This is the three-phase, and with three-phase, you get very little common mode voltage. Common mode voltage becomes the voltage between the frame of the motor and the shaft of the motor. When you put it on a VFD, you do not get these added up, and you, as you would here, they add up to 0 at any point in time. On a VFD, they don't. And so you end up with common mode voltages. The voltages are between the frame and the shaft of the motor. What is between the frame and the shaft of the motor? The bearing. So if those voltages get too high, they can arc through the bearing, and they begin to pit the bearing and pit the bearing race. You can actually measure these voltages with a device like this that has a brush that you can touch the frame, and you need to have at least a 200 megahertz scope, and you can see those voltages. Now, you can see here's a voltage that's going up, and then boom, it drops suddenly. Well, what causes it to drop suddenly? What causes it is it just discharged through your bearing. It just welded a little hole in your bearing, and it looks like this. You can't see that with your naked eye, but these little discharges, electric discharge machining, as you see, EDM, they create these pitting in your bearings. From the naked eye, the pitting looks like this. It just kind of makes that shiny bearing more of a matted type of finish. And if it gets really bad, then it turns into fluting. Once you get fluting, which is down here on the lower left, because it looks like the fluting on a Greek column of a temple or something, then your motor is going to be really noisy and it's on the verge of bearing failure. Well, how can you protect against something like this happening? First of all, if you send your motor in for refurbishment, rewinding, they need to cut that bearing and do an inspection. Here's various ways of protecting that. The first thing that seems to make a lot of sense to me is an insulated bearing. Now, this bearing over here is an insulated bearing. It's got an insulated coating around the outside of the bearing, or you could coat the frame there where the bearing goes into the frame. We have largely moved away from these because of the fact that if you have even a little scratch in there, then that doesn't work, and you can still get capacitive currents through there. So we really prefer a pure full ceramic bearing. In these cases, the bearing balls are actually ceramic. They're not steel. And these work fantastically well. They also last probably 10 times as long as a standard bearing. You can look at this later. This is a list of all of the characteristics of a ceramic bearing. They're great bearings. And last time I talked to our motor shop guy, he said if these are installed correctly, they've never had one fail. And they're very quiet. They are smoother. They're great bearings. Why don't people use them? Because they're expensive. The other technology we're using is shaft grounding. In this case, and let me show you a picture. You have a shaft grounding ring here, and it literally shorts the shaft to the frame. So we're basically shorting that shaft to the frame and thus limiting any voltages from building up. The big advantage of shaft grounding is it's a lot less expensive than ceramic bearing. There are different ways to mount it. Recommendation is, and let me do this, then I'll come back to that slide. Put one shaft grounding ring on the motor. Generally, the driven end is best up to motors 100 horsepower. If it's over 100 horsepower, we recommend an insulated bearing. I say we, that's Aegis. They're the only manufacturer of these bearings, these shaft grounding rings, I mean. And then a shaft grounding ring on the other side. And in quite large motors, we're finding that we actually have to use 2 insulated bearings plus a shaft grounding ring. Now, let me mention, when you use that shaft grounding ring, we highly recommend that you make sure the shaft is smooth and you use a colloidal silver shaft coating where that brush touches it. And that gives it much better conductivity. Last thing I really want to talk about here is cable selection. This is from ESA, the Electrical Apparatus Service Association. They say for an adjustable speed drive, you should use an inverter duty motor. We talked about that. That has to do with the insulation. You should use supply conductors designed for ASD circuits, and you should use some form of bearing protection. So the last thing we need to look at is cable recommendations. Recently, cables, special VFD cables from the drive to the motor have become much more popular, and most manufacturers of motors now are actually recommending that you use this. Let me show you the inside. If you have a good cable like this, the cable, the three phases is symmetrical in a triangle shape. Instead of having one ground, you actually have three grounds. Some VFD cables only have one ground, but the best is to have three grounds. And then you have an overall cable sheath. So this keeps the voltages balanced. It will help you with your bearings. It will keep the motor windings balanced inside, and it will help prevent radiation of that PWM noise going airborne through the cable. So most people installing drives do not use this, but I do recommend it, and of course ESA recommends it, so there's kind of an official recommendation. There's some more pictures. That's medium voltage VFD insulation, and this is a table which is very good. This is from T-Mike, Toshiba, Mitsubishi on their medium voltage motors, but it also has one for low voltage motors, and it tells you what cables are acceptable going from your variable frequency drive to your motor. So I'm going to stop here. There's some other stuff on medium voltage drives, but we're going to have a special class on medium voltage drives, and so I'm not going to cover that today. So I am done, and I'm turning the time back to Tyler.
Great. We do have a couple questions. Let's go ahead and start with one. Are there any calculations for how much heat is being dissipated in a VFD?
That's a very good question. Certainly calculations are possible, but let me say this, the efficiency of VFDs are basically the same because they're all built the same. They have 6 diodes, they have a capacitor, and they have IGBT. So the efficiency from one drive to another is not that different. You will find that the efficiency of larger drives is a little bit better as the drives get larger. So the efficiency of a small drive, 1, 2, 3 horsepower, is probably 96%. And then as you get higher, they get into the 97%. In terms of the calculations, we don't have a specific formula for that. I suggest just going to the manufacturer, and they will generally have listings of the losses in that particular drive. But without knowing the conduction losses versus the switching losses and so on, there's not really a simple calculation that I've ever seen.
Great. If my motor has a 1.15 service factor, how will it act with a full load while on a VFD? Will it still have that service factor? Also, what motor data would you need to input to the VFD?
Yeah, so what motor data would you input to the VFD depends on your control system. If you're running in just PWM volts per hertz mode, which is the way we run most drives because it's very simple to set up, and if somebody replaces the drive or replaces the motor, it still works fine. And in that case, all you really need is the rated voltage on the motor and the rated current on the motor. If you want to run the motor in flux vector mode, now you need all kinds of stuff, and you need information that you simply are not going to be able to get because the motor manufacturer is not going to give it to you. So drives that do that actually have a self-tuning algorithm that tunes the motor and puts in all the various resistances and reactances and so on inside the motor, in the rotor and in the stator, and that will tune it for you. But and that gives you better performance. The thing I worry about is when you replace the motor, then that new motor could be different than the one that was there before, and I worry about the person replacing the motor not realizing that now they have to retune that drive to that new motor. So there's my 2 bits on that.
Great. What kind of audible sound does the drive make at 2 kilohertz versus 6 kilohertz? Can you please provide your best impersonation of the sound?
Oh, this is bad. Let me go back. I realized I didn't answer one part. They said if you're running the motor at a service factor motor, do you still have some service factor? According to NEMA, no. You lose your service factor, and that's because as the motor slows down, you have increased cooling and you're using your service factor there. On the other hand, if you are actually running at 60 hertz, truthfully, you probably have most of that service factor that you could use. And as long as the motor is running cool enough, then you're probably okay. In terms of carrier frequency, yeah, I'm not a great impersonator and I don't have perfect pitch, but at 2 kilohertz, if you listen to the motor, it's probably giving you a sound kind of like ee, ee, something like that, maybe a little higher. Ee. When you go to 6 kilohertz, it will be a lot quieter, but it'll be higher. So something like that. It'll be quieter, but higher. So I apologize for my poor impersonations.
All right. How do you interface with a VFD through a cloud platform? Is it possible? Specifically, they're referring to Industry 4.0.
Yeah, this is something that's going to get really too complicated to answer here. And so we may have to answer that offline a little bit. VFDs have a number of communications available to them. The most standard is Modbus, and I think probably most VFDs will communicate Modbus for free. Ethernet is getting much more common, and so drives capable of doing Ethernet are more common, but most good sophisticated drives, you can put cards in there that will allow you to operate on LawnWorks or Profibus or all kinds of stuff. So drives have an impressive array of communications capabilities. When you're going to operate across the cloud, now, of course, security becomes your biggest risk. And that's where the answer gets a lot more complicated.
I think Paul Rossiter also had an answer that he wanted to chime in on this. We'll see if he can provide any input.
Yeah, Tyler, I was just going to mention that this is actually something we've experimented with a number of different drives, whether it's the Mitsubishi drives or the Gulf drives that we represent. And we've experimented with tying in vibration monitoring from the motor back into the drive through the internal PLCs to the drive. But it does come back to the communications to get back to the cloud, like Craig has mentioned, whether it's Modbus, TCP/IP, or Modbus RTU. You can typically tie those back into some kind of gateway that's going to give you more information. But there is, depending on what you're trying to do with the drive, would kind of lean towards which way you're going to go. But there are a lot of neat things happening with drives right now as far as tying them into Industry 4.0, whether you can get, some of them are starting to get diagnostic data and lifetime health data of the drive that's being tied back into cloud systems. So there's some neat things that can be done, and we've even really pushed towards how can we show the health of the motor and the drive at the same time. That's something we're actively working on too.
Great, thanks, Paul. Moving on to the next question. Is it true that the NEC 2020 is changing the requirements for electrical protection?
That's a good question. I mean, I'm not sure that I completely understand the question. Electrical protection. I guess if there are some requirements, I'm not aware of them, and there may be.
Okay, great. Have you had experience in documenting energy savings from conservation voltage reduction on the AC side of the drive? Are there any savings?
Yeah, there are definitely savings. And for instance, on the drive that we most use, you can simply go into the drive and it will tell you the input kilowatts and the output kilowatts. And there are savings, and they're legitimate, but they are small. And so remember that a motor is probably 95% efficient. You've only got 5% losses to contend with there anyway. And if you lower the voltage, you're going to see a slight increase in current. So you might see a 1% saving, something like that. And I haven't done a lot of experimenting with this, but I would say the savings are real, but small.
What is the purpose of the DC link reactor?
The purpose of the DC link reactor. Excellent question. This is going to be covered in great detail, not in our next session, but in the session after that on harmonics. The main reason for a DC link reactor is the same as the main reason for an AC link, not link, but an AC line reactor, and that is to reduce harmonics. So on a drive with no DC link reactor, no AC line reactor, you're going to get 70, 80, 90, 100% harmonics on that thing, total harmonic current distortion, and that's pretty bad. So we put in those reactors, and they typically will reduce your harmonics, which is basically high frequency noise, to 1/3 of what it is without the reactors. Now, AC line reactor can also provide surge protection. The DC link reactor does not. A DC link reactor, if it's going to be standard in the drive, also actually allows the manufacturer to go with some smaller diodes and smaller capacitors. So there are some, if you're going to have it there anyway, there are some savings in your materials by using that. But for the most part, it's there for harmonics.
Do any manufacturers allow you to specify motors with higher capacity having 2 insulated bearings compared to 1 insulated bearing and a shaft ground bearing?
Yeah, that's very common, and you can, depends on the size of the motor. You know, if you're getting into large motors, you can specify anything you want and the manufacturer provides it. In a lot of smaller motors, you're just taking motors off the shelf, and what we typically do would be to modify that motor before we send it out. But certainly you can specify motors from your supplier that will contain a shaft grounding ring and or ceramic bearings and a shaft grounding ring. It's pretty common.
Craig, wouldn't that also, you could easily have an issue if you do not include the shaft grounding ring, though, and put the 2 insulated bearings. Those currents can easily travel into the load if you're not isolated between your couplings, right?
Thank you, Paul.
If you use a sine wave filter, do you still need to use VFD rated cables to the motor?
Yeah, very good question. My opinion is probably no. A sine wave filter is very expensive, but the difference between a DVDT filter and a sine wave filter is a DVDT filter is meant just to keep your voltages below 1,000 volts, but you still have the PWM waveform. A sine wave filter, much more expensive, but it actually gives you a sine wave to the motor, and so there really would be no more reason to use a DVDT, or excuse me, a VFD rated cable on that type of system than if you just had an across the line motor. So haven't been asked that question before, but that's my opinion on the subject.
What are the conditions where you would need a DVDT filter under 100 feet?
Generally, if it turns out that you have a system in which your voltages at the motor are higher than 1,000 volts, then you're going to need to add a DVDT filter. And if you've been in this business for a while, you know that whatever rules of thumb you use, there's always going to be something that doesn't comply with those rules of thumb. So we have seen these voltages go higher, but you wouldn't know that unless you actually measured them. The main reason why I would put a DVDT filter on a motor where the lead length, or the length of the cable between the motor and the drive is less than 100 feet, is if the motor had standard insulation, meaning it did not have that high spike wire, it was not a VFD rated motor. in that case, then we would want a DVDT filter to keep those spikes under 1,000 volts.
Generally, are rear heat sink drives one continuous piece, or do the drives bolt to a heat sink?
Let me think. I'm trying to think if I understand that. Basically, the heat sink comes on the drive, and there's a flange on the drive that allows you to push that heat sink on the back of the drive through a hole in the cabinet, and then there's a flange that's kind of mounted on the drive between the heat sink and the drive, which allows you to bolt it on the back of the cabinet. And then you will, of course, have fans on the heat sink. So I hope that answered that question.
What are vector flux drives?
Vector flux drives. So when we did our motor presentation last time, we said you want to keep constant volts per hertz. And if you do that, you get a pretty good operating drive. But if you want to actually get into drive theory, then there is a direct axis and there's a quadrature axis in the drive, and one controls your flux in the drive and one controls your torque out of the drive. And so you have to have a very high-speed microprocessor that knows all of the parameters within the drive, like your leakage reactance on the stator and your resistance and the flux in the iron and so on. It has all these things that you get when you self-tune the drive. And then it actually goes through a matrix, and it actually attempts to control that quadrature axis and the direct axis separately. So in most drives, if you said, can you control torque in a drive? I would say, no, not really. The torque is whatever the motor requires. But if you get into something sophisticated, like either a closed loop flux vector, which requires an encoder on the motor, or an open loop flux vector that does not, you actually can control torque with those things. And you can also get very, very fine speed regulation. So typically your slip on a motor is maybe 1-2%. We've seen some of these open loop flux vector drives control speed within like 1/10 of a hertz, which is just shocking to me. But anyway, that's what it is. You're attempting to calculate it in order to control the actual magnetic flux and torque inside of the motor. And if you want to know more than that, then you can look that up on Wikipedia or just Google and try to understand the theory behind a flux vector drive.
When running multiple motors on one VFD, what type of motor control must be used by the VFD, scalar or vector?
Yeah, when you're going to run multiple motors on a VFD, you need to use scalar control. Now, scalar control would just be your standard volts per hertz, because if you're trying to use a flux vector control, it's trying to actually control the inside vectors in that motor, and you can't do that with multiple motors. So anytime you have multiple motors, you want to go with a standard scalar volts per hertz control.
When you have a drive inside a cabinet with a fan providing cooling to the cabinet, have you considered fan failure on the reliability of the drive system?
Yeah, certainly that is an issue. So there are two fans. There is, or maybe I should say two types of fans. There are fans on the VFD chassis itself, and then there are fans on the enclosure. So on the VFD chassis itself, some manufacturers, certainly Mitsubishi that we sell, they actually have 3 wires coming back from the fan. So as the fan turns, it sends pulses back to the circuit board, and those pulses tell you that the fan is turning. Now, not all drives have that, but in that event, if that fan stops turning, you will get a fault on the drive. The fans on the enclosure, we generally provide a redundant fan, so you could have one fan fail and you would still have sufficient cooling. And if the fan isn't running at, or if the drive isn't running at full load, you may have more redundancy than that. In that case, the only backup you have there to fan failures is an over temperature in which the drive would shut down on over temperature. And so certainly maintenance becomes an important factor there. You need to go through and you need to look at your fans periodically and make sure that they're all turning. But with that redundancy, we found that we don't really believe there's a real reduction in reliability with those fans on the enclosure as opposed to just putting the drive on the wall. In fact, we believe that because it's clean and lasts longer, there's actually some improvement in reliability.
Can you perform maintenance on a drive, or is it too complex? Same question for a repair if it fails.
Yeah, that's a great question, and my answer is depends on you. If you're not an electrician and maybe you're an operator and you're scared to even get into the drive, then I'd say don't. On the other hand, if you have an interest in this, then absolutely. It is very easy to test the diodes to see if one has failed. It's very easy to test the soft charge circuit. It's very easy to test the IGBTs. And drives are certainly repairable because we do it all the time. So the answer to that question, I think, is best. Tune into our next webinar and we will show you how to do it.
Oh, sorry, it might have been on mute. What are the recommended speed ranges of a VFD?
So this depends a lot on all kinds of things. In general, a good quality TEFC, total enclosed fan cooled motor with 1.15 service factor, and not all of them, but most of the really good ones, you can go from 25 to 100% speed at constant torque, or you can go from 10% speed to 100% speed on variable torque, in other words, a fan or a pump. Now, that's mostly dependent on the motor. If you want to go over 60 hertz, you just need to make sure that you don't go over full load amps and that you don't get vibration and that the bearings are suitable for that, which they generally are, as long as you go a small amount over that frequency. In terms of slow speed, you could go slower than that at constant torque or variable torque, as long as you have some form of cooling for the motor, like a non-ventilated motor or a fan-cooled motor in which you have a blower-cooled motor, I guess I would say, where you have an external blower that keeps that air moving at full velocity regardless of how fast the motor's going. That would be in lieu of a fan on the shaft of the motor. And that's fairly common. Then you can get down to some very, very slow speeds. If you want to go extremely slow, then you're going to need an encoder on there because I probably wouldn't. If you have flux vector mode, you could probably go down to around 1% or so speed, and I would feel fairly comfortable with it. But if you're inching along, you're going to need to use an encoder, and you're going to need to use closed loop flux vector.
Where do you suggest power factor correction and or harmonic filtering in the system circuit? Does it go after the VFD and before the motors?
Yeah, so harmonic correction, of course, goes on the line side of the VFD. And this is a subject that we're going to get into in great detail in a couple more sessions. But it really depends upon the system. In general, we would think for larger motors, the best place to put harmonic correction is, was that about harmonic correction or capacitors? Maybe
they had said power factor correction and or harmonic filtering.
Oh, and or harmonics. Okay, so addressing the harmonics on large motors, it's generally nice to put the harmonic correction right at the motor. And there's several ways of doing harmonics, which is a subject of a whole class that we're going to teach in a couple of times. If you've got a number of smaller motors, or you've got an existing system that you want to correct your harmonics, then a lot of times a bus-mounted harmonic filter is best. In terms of capacitors, don't ever put capacitors between the VFD and the motor. And I suggest that you have a little bit of impedance between any capacitors and the VFD, because they can increase your peak currents, depending upon what system is there. And so I'm not saying you can't put them right at the at the drive terminals on the line side, but I would suggest putting them either a significant cable distance away or on the other side of a transformer. I think that's the best way to go. But of course, when we look at specific systems, we know what we like is the best, and sometimes we compromise because we have what we have, and we just have to deal with what's there.
Is bearing wear and pitting a concern for all VFD-driven motors, or is this a particular concern for certain cable lengths, locations, etc.?
Yeah, I would say it's a concern for all VFD motors. And certainly if you use, if you have a sine wave filter, for instance, it's much less common. If you have VFD rated cable, it is less common. But we would still say, other than with a sine wave filter, no, it's pretty much universal, and there's no way to really calculate it and decide whether you need that or not. So we would recommend it on all motors. Now, having said that, a lot of times people don't do it and the motors run forever. So you can't really tell for sure. But if you want a really reliable motor, we would highly recommend doing that. And that is also an ESA recommendation if you want something official.
You did not cover the use of sine wave filters to reduce bearing noise, although this was shown on the slide. Do you think that this filter is not a reasonable solution?
Yeah, I don't think it's a reasonable solution because, number one, it's not 100% effective. Number two, it is a lot more expensive than other ways of protecting those bearings. Now, we love sine wave filters, and we recommend that you always use a sine wave filter on submersible pumps. You know, submersible pumps, they're down there. The insulation system is not as great as you wish it would. They've got these flat cables sometimes, which causes problems. And so it's also very expensive to replace a submersible motor, particularly ones that get down deep. So we recommend that you have a sine wave filter on all submersible motors, even though it's a pretty pricey option. Other than that, unless you have extremely long cable lengths, we tend not to recommend the sine wave filter just because it's pricey.
How do you know the natural frequency of the motor when we operate through the VFD so as not to operate close to the natural frequency?
Yeah, so if you, in theory, you could have a mechanical engineer calculate the resonant frequency there, but I don't see anybody ever doing that. Generally, what we do is we do this at startup. And so we would run the VFD at 1 hertz, then 2 hertz, then 3 hertz, then 4 hertz, and we'd take it through its entire speed range. And we'd look at the load, whether the load be a motor or a fan or something else, and some type of vibration device. Sometimes that vibration device is just you putting your hand on the motor. But ideally, we'd like something more sophisticated that would actually look at the vibration. And then let's say you have a vibration, a resonant natural frequency that occurs. It starts at 33 hertz. So as soon as you go above 33 hertz, you start seeing the vibration. And when you go above 35 hertz, then that vibration would go away. Pretty much every variable frequency drive that I know of has the capability to program out those frequencies. So you would just program out that band of frequencies between 33 and 35 hertz, and then the drive would operate either at 33 or at 35 hertz anytime the speed reference is telling it to operate between those two frequencies. And that prevents you from operating at a natural frequency.
Great. Looks like we have one last question. From harmonics perspective, is there any advice in regards to connecting to station grounding systems?
Very interesting, to station grounding systems. Harmonics can be very complicated. And so I would say in general, when we're simply looking at reducing harmonics to an acceptable level for IEEE, we don't really look at the the grounding system as a way of mitigating or exacerbating harmonics. But I'm not saying that in certain instances that the way the thing is grounded may not end up being a factor. In general, we just would recommend having a good ground, both on the frame and on the power system supplying the VFD. Although VFDs can operate on ungrounded or resistance grounded systems.
Great. Looks like that's all the questions we have. So we wanted to thank everyone for joining us today, and we look forward to seeing you next time.